This poster covers electron subshells as equal to a Bose cylinder in two hemispheres, that also being equal to Slater type subshells. Specifically, we're going to drill down to equatorial distribution in subshell 3D and make that a special case as a Gaussian type subshells, not Slater. Now, as I look at electron distributions, I see these with the center of these as longitudinal surfaces, that those electrons are Bose cylinders. Specifically, though, there is a different one that is equatorial. So subshell 3D has both an end cap, like a rim of the end cap of a cylinder, but it also has an equatorial one. And what I should find from my calculations is those are not Slater type orbitals, but are Gaussian. So it will lead me to the eventual question, how can we have different angles and there being different subshells? Now, this Bose two-cylinder, I calculate as 4 vectors as the basic cause of subshells. There are 2 radial and 2 axial, which balance until there's a position where the electrons want to be away from this axis and spaced. So this Bose cylinder surface with ×2 for hemispheres polarity is how it was described by Bose in his 1924 paper that led to his winning the Nobel Prize. So the radial forces are inward, electroproton electrostatic force, opposites attract. But an extra 1/r, which I interpret as the strong nuclear force, as radial outward. On the axial direction, we have the weak force, which is inward towards a axis. But then you have multiple sets of these electrons, and those provide electron-electron electrostatic repulsion. Now, because those are many particles, those also generate statistical mechanics. And until you have this Bose cylinder, you do not have statistical mechanics and quantum behavior. This 4-cylinder is in balance. Now, also understand that there's a second set as a poly pair offset by 1/2 phase to give you the 190-degree angle. Now, that Bose 2 polarity is because of these 2 radial forces. There's the inward electrostatic and the extra 1/r that keeps a wall of repulsion that's somewhere around Bohr for the hydrogen atom. As a result, electrons, like kind repel, want to be as far away from each other as possible. Thereby, they take the 180-degree positions. Now, here's the special case. When you have a cylinder, but the distance is 0, those radial and those axial are also radial. You see, they're at the 90-degree position, which makes them exactly the same as those original radials. So here, the 4 vectors act as if all radial, and so Gaussian. So it does not display the behavior you find in Slater type orbitals and the derivatives that generate the statistical mechanics. Now, overall, this logic will change the off-ball rules, the strict ones that we go by. You see, we have 3 types. We have the longitudinal rings at less than 90 degrees. Those are both radial and axial and are Slater type orbitals. The equatorial is radial only and Gaussian types, and subshell S, also 2 at the poles in the other way, is also radial only because there's no axial electrons, others. It's only 1 in each shell. So that means I recommend that overall we change and separate 3D into both the Bose part, the Slater type, and the equatorial as Gaussian, and state them separately when designing electron configurations, and especially their exceptions.